Okay, you're gonna start when you.
Okay. Good afternoon, everyone. So this time, let us continue with electromagnetic transitions and the form factors on our journey of Mesons on the light front. So just a quick recap. So last time, so I'm saying that with the light front Hamiltonian formalism, we'll start with the QCD Lagrangian and and do the canonical quantization to get to the QCD Hamiltonian, the light front quantum field theory. And then in calculating the Meson states, so one could also get some inputs from the phenomenological study and get the effective Hamiltonian. And then putting this all together to get, so P minus is the operator, and to get the Meson state when solve the eigenvalue equation. Okay. And then this time we will look at, so with the obtained Meson states and in terms of light front wave functions, how we can study observables of physical quantity. Okay, so first let me write down the state, the Meson state in terms of light front wave functions. So for the Meson, we start with the simplest non-trivial case, that is to truncate the Fock space into the leading Fock sector, the QQ bar Fock sector. So I'm writing down, so let me write down the vector state, the state vector explicitly. So we will use this later also today when we look at the form factors. So if you're looking at notes, so this is equation 54 of the part 1 of the notes. So I'm using the relative coordinates, so k perp and x. So this 1 over square root of NC is the color factor for the Meson state. So since it's a color singlet, and then since we have the creation operators. Okay, so writing this out will also fix now convention and the notations. So, and what is the light front wave function here? So this coefficient that in front of the creation and annihilation operator, so that's the light front wave function. Okay. And so if you are using a different convention, for example, in different works, and it does not matter, so you change the corresponding like expansion coefficients in front. So what matters is that like writing down this, so you fix the definition and the convention of how your Meson state is represented on the Fock space. Okay. And let us also write down the normalization condition. So, and then, so this is for the wave function. And so with this, the state. It's normalized as this. Oh, I forgot the G here. That's the total spin. Okay. So this is notation. Okay. So now let's start our topic today about how to look at a certain observables. So the process, also one interesting process to look at is to use an electromagnetic probe to detect the internal structure of the Meson bond state. So if we think about the virtual photon that is scattered in the Meson state, the initial momentum P and the final momentum P prime. So this process is like you have the virtual photon is like a probe, and it could, so this is the initial Meson, and that's the final Meson. So they are the same kind. And for example, experimentally, this would be something like you have an incoming electron, that here the Meson could be pi plus. Okay. And this kind of experiment could tell us some structure of the Mesons. And very similarly, so if now my initial and the final Meson are different, so, and I look at the process like this. So initial, I have Meson A with momentum P prime, and the final Meson is a different kind of Meson B with momentum, P. Okay. And then, so the photon would carry away some momentum, and also here. And for example, experimental process would be like a J psi decay into eta C plus the photon. Okay. And so both process could help us study to say what's the internal structure of the Meson is like. And let us write down the amplitude first. So a relevant amplitude is this. So let me just write down. So this is the final state B. And with the G mu, that is the electromagnetic current. So this applies to both process. For the left one, which is the elastic one, it's just you have both A and B equal to H. Okay? And so let us write a shorthand notation as MG prime. Okay. So MG is just the magnetic projection of the total spin. So here I could actually should slip in G and G prime. So for example here, so G psi is a vector Meson, so it's J equal to 1. And so eta C, you have the pseudoscalar, so it's J equal to 0. Okay. And so this quantity, this I, is known as the hadron matrix element. And as you can see, it can be directly connected to the scattering amplitude. So if I'm looking at the scattering amplitude of A to B plus the virtual photon, so Q is the transverse momentum carried away by the virtual photon. So what I need to do is that I just contract this I mu hadron matrix element to the polarization vector of the virtual photon. Of course, the photon could carry its own spin, that's called lambda. And so with this M, it also has the information of the spin of each particle. Okay, I just did not write it out explicitly. Okay, and so the thing that so with the theoretical calculation with lifelong wave function, we can evaluate this I mu and then the scattering amplitude. So we want to compare with something that experiment could measure. So what the experiment measure is actually the decay waves. So that's something experiment can measure. So for example, from meson A to meson B plus photon. And so the connection from the scattering amplitude to the decay waves. So that is straightforward. So you integrate over all the final state, and then you average over the polarization of the initial state. So summation of m prime and lambda. Okay, and you can find this formula actually in the PDJ book. And note there's something here is that this decay width is a frame dependence. So this formula is actually given in the A rest frame. Okay, so now this is nice that we can use the wave function to calculate this quantity, and we can compare with the experiment or make predictions of the unmeasured state yet. But as I told you, so this is depend on frame. So it would be good if we could have some quantity that have less dependence, does not depend on frame independent. And also, so this decay width is evaluated only at only when the photon is on shell. So, but what about when Q square? So that's the momentum carried by the photon when it's not zero. Because what we want to know actually is the internal structure of the meson, and it should not depend on frame, right? And we want to also get more information when the Q square is not zero. So to achieve those purposes, that comes in the study of the form factors. And so for this process, when the meson does not change, so that's the form factor there is the elastic form factor. And for this transition process, the form factor is the transition form factors. So in the next, we will try to address two key questions. The first one is, what are form factors? And secondly is how to calculate form factors from lifelong wave functions. Okay, let us address them one by one. So first, to see what form factor is, we need to do something called Lorentz structure decomposition of the hadron matrix element. So this I mu is what is defined here. Okay? So before we actually doing the decomposition, let us understand what like constraints or what properties it have. So the first thing we look at is the space-time translation. So let me first write down the definition for it. So what is this J mu, and written explicitly is the psi by x gamma mu psi x. Okay, and doing a space-time translation, so let us insert the write differently. So what is this? So this is written differently. It's like, so the P hat is the momentum operator. Okay, so if I put it back in here, so these two, you will see, so they will become one identity because they're only gamma mu in between. And so this acting on the final state, and this one let it act on the initial state. So what would give us altogether is an overall phase factor not on the difference of the momentum of the initial and the final Meson state. And what we are left with is just the G mu and 0. So now, oh, okay, sorry. So this psi is the fermion field operator, and so this psi h stands for the Meson state. It's not the same psi. Okay, so this is the phase factor, meaning that. So note that when we calculate this hadron matrix element, what it means physically is that when it contracted with the polarization vector, it gives the scattering amplitude, and then to the decay width, we square it, right? So if we're interested in the internal structure of the Meson state, so this phase factor will not make any essential contribution. Then, as you can also see in the study on form factors, we only need to look at this G mu 0, okay? And so we'll look at this in the following. So this is the first property look at. So the second one is the current conservation. So what is current conservation? So it can be written simply as partial mu J mu equal to 0. And what partial mu did is that it will bring down the P mu. Okay. So I'm not writing out all the momentum, but it should be there implicitly. Okay. So this is so this gives us a constraint on the hadron matrix element, and I will refer to this as current conservation condition. The third property is about charge. If you still remember in the first day in the Guillaume's lecture, he said that on the left front dynamics, so the current that gives the charge is the G plus. Okay, so we define charge as the integral of G plus over the space. And if I let this charge operate on the Meson state, it should give us the charge of this corresponding Meson state. And of course, the Meson state is the same because it's an eigenstate of this Q. And so what can this tell us about the hadron matrix element? So let us put the same hadron state, but with a different momentum on the, we act this on both sides of the equation on the left. So what we get is that on the left-hand side, so this Q is the integral of the J plus. So if I take the integral out on the way to the left, and what we have is, so J plus in between, and this, right? And on the right-hand side, so this EH is just a number, so that's the charge of the state. And what I get is a normalization of the state. And so on the left-hand side, so with what we have seen from the first one, so this would give us a phase factor. And if I integrate out phase factor, what I get is also a delta function. And then with J plus and 0. Okay, so I can get rid of the delta function on both sides of the equation. So you can integrate over the p prime, and what left? So now I have the same p on both sides, same state. This is a normalization condition of the J plus current. So it's equal to 2p plus times the charge of the state. Okay, and let's refer to this as the normalization condition. Okay, so now we will see some properties and the constraints on the hadron matrix element. And what is the form factor? So the form factor is just a decomposition of this hadron matrix element into Lorentz vectors. Okay, because so this I did not write it out, but we've been writing it all the time. So it's so we've defined it here. So it's this one. So we know this quantity, the hadron matrix element, should transform under the Lorentz transformation and the Lorentz vector. So we should be able to decompose it into a linear combination of various or multiple Lorentz vector. And then the coefficient in front of those Lorentz vectors are the so-called, are the so-called form factors. Okay. And now our task is to find the form factors for a specific meson or specific transition. So let us do the simplest case is to find the Lorentz structure decomposition of spin zero mesons. Okay, so what are spin zero mesons? If I use the JPC notation, so the total spin J should be 0, right? And then the parity, the P, could be either plus or minus. So if it's plus, so this is the scalar, and the minus one are the pseudo-scalar. Okay, and then so these are for the mesons, and especially for quarkonia. There's an extra symmetry of charge conjugation. And for J equal to 0 particle, the charge conjugation is always 1. Okay, so those are the spin zero mesons. Now, since we are talking about spin zero mesons, so I will not write out this J and MJ because it's always 0. And I will only keep its momentum. So I can write it into, so EH is this charge, so this is just the coefficients to some x mu. Okay, so this x mu should be some vector. So to do this decomposition, we first need to find out what are the candidates of x mu. So if you think about this process of a photon that, of course, the photon is not entered here yet because that is the polarization vector that to be contracted with J mu. So in this process, what comes in are the momentum of the initial and final photon, right? So naturally, the candidate for the x mu are p mu and p prime mu. Okay? And then, so those are the vectors, but we also need to know what are the relevant scalars. So this is finding the argument of the form factors, because the form factors should depend on something, right? And those should be the Lorentz vectors. And let's see, scalars, sorry. And what are the relevant scalars in this scenario? So we have the magnitude of p prime and also p, and also the dot product of p prime of p, right? So this could be the possible arguments of the form factors. But so we have three, but the actual free one is only one, because we are not thinking about the mesons and they are on their mass shell. So the mass shell condition tells us that we can fix the value of p prime and p. And then the only free scalar that the form factor can depend on is just this, the p prime dot p. So let's change our variable so that we can write it in a more compact and elegant way. So this p and p prime, let's write it as q mu equal to the difference and p with a bar on top equal to the summation. Okay, and you already know the physical meaning of q, so that would be the momentum carried away by the photon. And then, and of course, we know the q square by doing the square of the difference on the p prime and the p, and also with the shell condition. So we have this, and similarly, the p bar prime photon is like this. Okay, so this means I can, so the form factor depends on the p prime dot p, and you see from this relation that the q, we can also write p prime dot p in terms of q square, right? So this means I can write my form factor in terms of the q square. So the form factor would depend on only one variable in the q square. Yeah. So now let us write out the x mu, the structure we want to find out with our all possible candidate. So, but with this new set of variable. So q mu, and let's call its coefficients h for now. And for the p bar, let's call its coefficients f. So what I'm doing here is essentially decomposing this hadron matrix element. Okay. And now, but we are not done yet. Recall that in the beginning we discussed some constraints on the hadron matrix element. So the first one is, if I'm going to apply here, is the current conservation. So 1 to 0. So if I do the let us just go back and see what we have there. So you see this would bring down the p prime minus p mu and contract it with this hadron matrix element, right? And with the new variable we have, this is just the q mu, right? So if I if I plug this x mu in this equation and apply the current conservation relation, what I have is I have mu squared plus q mu p mu equal to 0. Okay, so this means no, though it appears that I have two form factors, but their dependence between them, so I only have one independent form factors. So with this, I can write h in terms of f. and then put band into X mu. So I'm just putting it back into the equation we're starting with. Okay. So now we have the now we find the Lorentz structure of this hadron matrix element for spin zero method. No, but there are more conditions that we need to check. So for example, so this one should be, let's check the hermeticity. If I take the Hermitian conjugate of it, so meaning if I put psi h to the left hand side, and of course I have complex conjugate, so this should be stay the same because it's Hermitian. And what does this tell us from this equation is that fq square is real. Okay, so we have form factor and it is real. Okay. So when we are making this derivation, we keep in a generic term that the H prime can be one meson and H can be a different meson. Now for the elastic process, when we look at elastic form factor, the initial and the final mass are the same, right? Meaning H prime equal to H, and of course their mass is the same. So this means this term would vanish, right? So for the elastic case, the relevant Lorentz vector is the, this is a total momentum, and then there's only one form factor of Q square. And now we have also discussed the normalization condition. And what this tells us is that this form factor and Q square equal to 0 should be 1, right? So we've just seen that. So here, normalization, the normalization condition is that you take the plus component, right? And it should give you 2p plus times the charge. And here, if you take the plus current, so this p bar would give you 2p plus when q is equal to 0. So this gives us a normalization condition that tells us f0 is equal to 1. Okay, so this is for the elastic form factor. And let's see more about the constraint and properties that the form factor should satisfy. First, let's look at the parity. So let's call this equation 1.1. Okay, that's the form factor side. So 1.1 left-hand side, if I put in the operation of parity, let's see what we will get. So now I will also write out the parity of the Meson state. Recall that when I introduced the spin zero Meson to you, that the spin zero Meson could either have parity plus or parity minus, right? So let me also write out the parity of the state. And let us plug in a complete set of the parity operation. Okay. And what the parity operator did on the state with the momentum and the parity is that it will give you the parity of the state. So this is the parity of the state. And also at the same time, it will make a parity transformation of the momentum. And what the parity operator did to a vector G mu is it will make the transformation of the G mu also. Okay. So if we put this all together, so what we have is that, so this to the parity operator on the initial final state will drag out the parity of the initial and final meson, right? And then the action on the G mu. So let me take this out explicitly. So I also have this, and then so I'm just writing this as a dot product. So this is parity. Okay, and then so because I want to find some constraint or property of the form factor, so here let us plug in again the equation 1.1. So that is this. So apply the corresponding relation there. And but note that this P prime has a transformation and this P also has a transformation on it. So if I write it all together, so what I have is that I have P mu P nu rho Q square. And so both this P is the operator of the parity, and I know that, so its inverse is also itself. Okay, and so actually, if I write it out, the matrix form is like this. Okay, explicitly. So this would give us this together, just the delta mu rho. So meaning if I apply this to here, it will switch this rho, you replace those rho with mu. And so to compare with, so I start with the left-hand side of equation 1.1 and I end with, what I end with should equal to the right-hand side of equation 1.1, right? But what I see is that if I make this comparison, I get this extra quantity. So this means the product of the parity for the initial and the final meson should be 1. So this means if you are looking at the transition between the spin 0 mesons, it could only happen between a scalar or between pseudo-scalar, but I could not have transition that spin the parity. Oh, so this is not allowed. Okay. And another symmetry we want to check is the charge conjugation. Of course, this only apply to the charge neutral meson. So I will write the operator as this C hat. So for Quenching, let's start again with the left-hand side of equation 1.1. So just as what we did with the parity, so I will write it out the charge conjugation for the corresponding meson this time. And let us insert a complete set of a charge conjugation operator. So the charge conjugation operator, when it acts on a state with a specific charge conjugation, what it will give us is the conjugation of the state. Okay, and it does not change the momentum, not like the parity one. But note the difference between the parity operator is that when it acts on the vector like G mu, it will give me the negative weight. Okay, so G mu is the electromagnetic current that we'll be looking at. So what this means is that if I would get a negative sign from this operation on G mu, and then I would get the charge conjugation of the H and H prime. And then, so I will not write what is in bracket. Okay, and of course this should equal to right-hand side of equation 1.1. So what does this tell us? This tells us that the charge conjugation, the product of the charge conjugation for the initial and the final meson should be negative one. But recall that for a spin zero mesons, if it has charge conjugation symmetry for the quaconia, it can only be one. So this means this condition cannot be satisfied. So what this tells us is that the transition between the quaconia for the spin zero one, whether it has a plus or minus parity. So this is not possible. Okay, so this means if I calculate the elastic form factor, for elastic form factor have H equal to H prime, of course the C1 and the C2 are the same. I cannot have them together as -1. If I look at the elastic form factor of a spin zero quaconia, it should always be 0. Right? So this is the conclusion we have by doing this vector meson production. But you will see that even though this is 0, we will still calculate some form elastic form factor of the meson state, as you might see in some work like for eta C prime, and even pi 0. So how does this happen? Let us now go to the second part. That is to calculate the, so we have addressed the first part. So the second part is how to calculate form factors from lifelong wave functions. So of course here we will only, when we look at the Lorentz structure decomposition, so I lead you go through the simplest case, that's for the spin zero meson, but I hope you get the idea of how to find all the relevant vector and the form factor, so you can apply the same technique to spin one. Okay, and of course the candidates here would be, you would have more vectors, and then for the same techniques also apply when looking at transitions like between spin zero and spin one mesons. So if we have time after we finish part 2, I will come back and show you what we can do for 0 to 1 transition. So but for now, let us go to part 2. So recall that, so to calculate the form factors from the lifelong wave functions, so let's zoom out to go back to what we start with is here. So we have known how to decompose this hadromatrix element into the form factors. So it's like we know form factor with some Lorentz vector. So we've already understand the right-hand side of the equation. So now if we can use the lifelong wave function to evaluate the left-hand side, then we can find the form factors in terms of the lifelong wave functions, right? So the way to use the wave function to evaluate the left-hand side is actually very straightforward. So we already know J mu, that is the electromagnetic current, the psi by gamma mu psi. And we have also writing out those psi, the Meson state in the form of the Fock space representation, so even for the QQ bar sector. Now, what we need to do is just putting all these pieces together. Okay, so let's do it now. So I call this lifelong wave function representation of hadron matrix element. Okay. So putting all the pieces together. So let me write down. And G mu explicitly. So what are the signs? So you will see that also in Guillaume's lecture. So when you do the quantization of the fermion field, so you can expand this sign in terms of the, you can write it as a mode expansion, simply referred to the Fourier representation. So let us write it explicitly. I mean, everything together. So we have psi bar. So I have two integral on the momentum because I need to do this both for psi bar and the psi. And I distinguish them by using the 1 and 2 index. Oh, so this is actually, you can find the expression for the fermion field expansion and equation 39, I think, of part 1 of the lecture. Okay. And then for psi bar, I have this. And then there are gamma mu in between. And then the psi. So that's the G mu in terms of the creation and annihilation operators and also with the spinors. So you see, writing this thought is actually very similar with the exercise I left last time because we did not have the time to do it. So that is to derive the kinetic energy for quark or for QQ bar state. So, and what is the P minus kinetic energy term? So of course there's an integral over the space part, and then you have this, right? And so you see this is very similar to what we are doing now. So if you want to evaluate this P minus, you just expand the mode expansion for the psi and the psi bar. Okay, so this is the operator, and now we put the operator into this hadron matrix element. And recall that when we're looking at the form factors, so with the space-time translation, so this X only gives us overall a phase factor. So we only need to look at G mu and X equal to 0. So now let's put all the pieces together only in the QQ for state only in the QQ bar sector. Okay, so I just putting so what we have written in the beginning, the expression for the Meson state. So I have 1 over square root of NC for both A and B. So together this is just 1 over NC. And IG are the color indices. So this is still for the Meson B. Now it's our turn for the G mu. So the purpose of writing this out explicitly is to see how we can contract the creation and annihilation operators and to see the corresponding physical process. Okay. So there are too many indices here for those creation and annihilation operators for the G mu. So let us use some shorthand notation. So for this B dagger on the 2, so I will just call it B dagger 2, and then this I will call U bar 2, right? And then similar, this is D2, this is V bar 2, and this is B1, this is U1. So this is D dagger 1, and this is V1. Okay. So what I have now is gamma mu. So it's just I put those I expand this product so that there gamma mu in between. And then the second term is I have a B dagger and a D dagger. In the third term, I have D and B. In the fourth term, since I'm writing it in the normal order, so I would get a negative sign when I put the D dagger in front of D. Okay. Now I finished writing for the G mu, and let's complete the expression by writing down the A Meson part. Okay, so now we can make some contraction between the creation and annihilation operators. So you see that we get 4 terms from this G mu, but since we are considering the Mesons only in the leading QQ bar Fock sector, actually only 2 terms survive. This term and this term. And so for the first term, how does it contract with the creation and the annihilation operator in the A meson and the B meson? So for this B2, I can contract with this B here. And then for B1, I contract this with the B dagger in the A meson. So this actually corresponds to the process that the photon is coupled to the quark line, right? And what left with the D is that the D in the B meson would need to contract with D dagger in the A meson, meaning that now the antiquark is just a spectator. So that's what this diagram, this term mean. And similarly, the last term is that you contract the D dagger and the D with the D and the D dagger in the 2 mesons, initial and final mesons respectively. And what you get is that now the quark is the spectator. And the photon would couple to the antiquark. Okay. So these 2 are the non-vanishing process when we only have the QQ bar component wave function. And then in between the 2 the 2 terms in between would vanish. But if we have the complete wave function of the state, meaning we have the meson state as an infinite expansion in the Fock space, then the second and the third term would not vanish. And what it means, let's look at what it means that, so if you look at this is B dagger and the D dagger. So what Fock component of the meson state would let it make a non-vanishing contribution is that in the initial meson state, I would have a quark and antiquark component that would couple to the external photon. Okay, and then what left is that for there's an actual quark and antiquark from the initial meson that would go to the final meson. It would all be a spectator. Initial and the final. Okay. Of course, I could have more spectators. So this would correspond to the contribution when I have the higher Fock sector contribution into component in the meson state. And then similarly, this term, the third term, is that you have, it's the opposite to what I draw here, is that you have the photon that is coupled to the correspond to the quark antiquark in the final meson. This is just one. All the other Fock particles are all spectators. Okay. So we will not have these 2 due to our wave function we are considering is just in the leading Fock sector, but we should be aware that what we are missing here. Okay, so now we are left with 2 non-vanishing terms. So the first term, so it's the photon is coupled to the quark line. Let me refer to it as the quark covered term. And this one, let us call it the antiquark term. Okay, so now we can simplify our expression here by writing the quark current and the antiquark current separately. So to write the quark current. So I already told you how we can make the contraction between the B and the D and their dangers. Let's write it out more explicitly. Is that so this B in the B meson would contract with the B2 danger in the current, and it would give us the following distribution. Okay. And so what the relation I'm using here is the anti-commutation relation between the B and the B danger. So for the expression you refer to, I think it's equation 42 of part 1 of the lecture. Okay. So, and of course you have this minus B danger BGS, but this would vanish when put it into the state here. And so I don't think I will have time to write out all of them, but you get the idea when you contract B and B2, then you get this delta function. And similarly, so the B1 is contracted with the B danger in the A meson, and this would give us the delta function on the P1. And then the spectator of the anti-quark would give us, I think this was writing out. So for P1 is similar than P2 one. We have is so recall that this IG as color, and then the S bar of the okay. So so we have 3 sets of this contraction, and we get the delta functions, and altogether we have 4 sets of the integrals over the momentum. So this would so applying those delta functions would let us integrate it over 3 out of the 4 sets of the momentum. And so what we are doing here is that let us first integrate out the X and the K. Let's see what we get here. So if I put this D and the D danger, so what I have about here, so this would let us integrate over X and K perp, and I would get just 1 over X, and then with the delta function, this tells us in the rest of the expression, I should understand X as 1 minus P plus, and the K perp is related to K perp prime. And of course, the color and the spin indices should stay the same. And then so for the other two set, so that's for the P1, so I'm writing shorthand notation. So you just give 1 and the one on P2. will also give us 1. Okay, so what I'm doing is just I insert the data function I get by contracting those B and D's back into this equation, but only looking at the quark counter term. Okay. So what I get in the end it's a rather compact form. So I still have the summation with S and S bar. So because I integrated over the XK perp and the P1 and the P2, so I'm only left with the X prime and the K perp prime. And then I still have the spinors. Okay, so but there's one thing that we need to specify is that so this X, recall that we defined it last time, is the longitudinal momentum fraction of the quark, okay, over the Mesons. So, and its value should in between 0 and 1. Of course, we disregard the 0 mole. So in between 0 and 1. So and here, so this means it should apply also to X prime, right? So my X prime should also be between 0 and 1. And from this delta function, so if I so this delta function meaning that when I integrate over X, so it gives me a relation between X and X prime. So when I require both X and X prime larger than 0 and smaller than 1, so you can check that by with this expression explicitly, that the X prime should be larger than 1 minus P plus over P plus prime. Okay, so this means, more strictly speaking, so the lower bound of this integral is actually not 0, but you should take the max value of 0 or 1 minus P plus over P prime plus. Okay, and so recall that we are evaluating this hadron matrix element as the process of A goes to B, right? So this means if you have the the photon in the final state, you would always have P prime larger than P. Then this means this value 1 minus P plus over P prime plus is so this is smaller than 1, so you get this value that is larger than 0. And on the other hand side, if you are considering a process like this, then your P prime plus is always smaller than P plus. And this means that your lower bound can always be 0. And so then the process, if you're considering like this, so but this is only a calculation techniques, then it would be more favorable, especially when you are doing the numerical integral over x, because it's always easier to integrate it over 0 to 1 rather than a quantity that depends on p to 1, right? Okay, so what left is that with this lifelong wave function representation for the hadron matrix element, our the second part of this derivation is only to put in the explicit expression for the spinor part, and then you would get the explicit form of how to evaluate the hadron matrix element with the wave functions. Okay, so this spinors would just be functions of the momentum and the masses. So for example, if I take mu equal to plus for the plus current, and S and S prime, so what you get would be P plus, P prime plus, and delta SS prime. Okay. So you can do all this with the mu equal to also the -1 and the transverse one, and you can generate a table with different S and S prime. Okay. And now you would get the everything you need to evaluate the hadron matrix element. Okay, so now let us review what we have together. Is that so? Sorry. Okay. So the two key questions. So we have addressed what are form factors, and then now we also know how to calculate the hadron matrix element from the lifelong wave functions and putting the both pieces together. So this is like putting the left-hand side of the equation. So now we know how to write this and the lifelong wave functions, and we have already know how to do the Lorentz vector decomposition in the first part. So putting these two together, we can get to the form factor in terms of the lifelong wave functions. Okay. So let's do this. And so before we do this, I want to talk something about the frames and the kinematics to have a better understanding of the process we are looking at. Isn't so if we consider process from A meson to B meson and with some X, so of course for the EM transition, so this is the photon. So, and we have already known that the form factor should depend on Q square, right? And the Q square is boosting environment. But what is Q square defined is that it's the difference between the momentum, the initial and the final meson. And this P itself is not frame independent, right? So it would be nice if we could write Q square also in terms of boost invariant quantities. So for this, I think I will just write down the expressions I have. But derivation is straightforward. You just plug in the expression for P prime and P. So the quantity here is that Z is defined as the fraction of the transferred P plus over the initial P plus. And this delta perp is defined as there's a nicer way to write it. It's let me see if I can work. Yes, is this. So the good thing is that both Z and the delta perp are both invariant. So recall that, so last time I showed you that you can check the booster transformation with a vector like this. So this is a transverse boost, for example. And you can check so the individual momentum, the P prime and the P, they would change with this boost, but the Z and the delta perp would stay the same when you do the transverse boost. Okay, so this is just a way to classify the frame. So you can think about, so Q is the change of the momentum transfer between the initial meson and the final meson. And if you picture it three-dimensionally, there are actually different ways to have a specific amount of momentum transfer. So you can either have the momentum transfer in the P plus direction, or you could have it in the transverse direction, or you have some kind of combination of the two. And so this Z and the delta perp quantify the how you distribute the momentum transfer in different direction. And so this we can we have defined the frame, and there are two special frames. You may already heard about this many times. So in other consequences, the Zhao-Yan frame, this is the this corresponds to the case where Z equal to 0. And then all your momentum transfer would be in the transverse direction. And of course, you can see here your Q square is equal to negative delta perp square. It's always smaller than 0. Meaning, so in the Zhao-Yan frame, you only have access to a space-like photon. Okay, if you're looking at the transition process. Then another special case, we call it a longitudinal frame. It's the other extreme compared to the Zhao-Yan frame, is instead we take a delta perp equal to 0. And then this means so in this classification, all the transverse momentum transfer is 0, and the momentum transfer happens in the longitudinal direction. And then the upper bound for this, for Q square in this frame is MA minus MB square. Of course, for elastic process is still smaller than 0, but for transition process, when the two mesons have different mass, the nice thing about this, we could access some information for a time-like photon, okay, when the Q square is larger than 0. Okay. I don't have much time, but I think with all those information, you can get already get the form factor. It's like, as I said, you have the hadron matrix element, and then you also have the definition of the form factor and what we did with the vector meson structure decomposition. So you can write the form factor in terms of the wave functions. So that's for the calculation in practice. But here now, I think it would be useful if we have some like a simple physical picture about what a elastic form factor looks like. Okay, so I think I can here. So here we know, so if we take the plus current, of course, you can also take transverse current or minus current, but I don't have enough time to cover that topic. So the current component dependency itself is also a very interesting study. So if I just take the plus current and then this part, I know it's just this, right? And then what I have as the form factor. So if I take the plus current, recall that what we get for the form factor on this side is divided by 2p. So that is actually p prime mu plus p mu, right? And if in the Drouin frame, their plus component is the same, so I get 2p plus, and this 2p plus will cancel with what happened here. So what's left with this form factor is just this part. So it's a convolution of the wave function. Sorry, this is the elastic form factor. The convolution of the wave function and with this actual 1 over x. And the convolution, so the difference between the two center of the wave function is, so one is k per prime, the other is k perp. And in the Drouin frame, all the momentum transfer is in the transfer direction. So if I think about this, if I picture this as a convolution, so I have k perp on the x-axis. So the A, so that's the initial meson standing somewhere here. And B meson standing somewhere here. So now, if I draw it's like a wave function. So I can kind of know, like, for example, we get some intuition from the non-relativistic quantum mechanics for the heavy system, like for a J psi. So for eta c, this has been 0. So the wave function should be something like this. B meson is something like this, right? And this is centered. One is at k perp, the other is at k perp prime. So if they are too far away, so meaning at a large q square large, then there's no overlap in between. So my form factor should go to 0, right? And when they start to overlap, so when these two are closely together, so I have some finite value for the form factor. And when they are exactly together, so what do we get? We have the normalization, just the normalization of the wave function, then the form factor should go to 1, right? So from here, without doing any actual calculation of wave function, we can kind of know that the form factor, the elastic form factor of a spin 0 mesons is something like this. Oh, of course, this is in the space-like region. So when you already define q square as the negative of q square, so the reason is just because q square is negative. And at 0, sorry, this is 1, and you have something like this. Okay, and then the slope of this form factor at 0 actually correspond to the charge radius of the meson state. So actually starting, you see that this studying the elastic form factors would actually tell us some internal structure of the mesons. Okay, I don't think I have time to do more derivation. So let me show you some result from actual calculations. So as I told you, like if you look at the elastic form factor, so here, like for example, eta c and eta b. So of course here we are plotting q squared, the negative 1. So it starts at 1 and goes down. And for the 2s state, since its wave function have a node, right? So it have a node when it goes down. And if you are thinking about the convolution picture that I told you, if you are convoluting two wave function that have a node, then in the form factor, you would also have a structure like this. Okay, so that's the elastic form factor, and we did it for the simplest case of spin 0 mesons. And as I told you, the same technique would apply to transitions. For example, in the N1 transition, so the transition between spin 0 and spin 1 meson. So this would tell us some, like the overlap of the wave function between two different meson state. And with the same technique, one could also one could actually study various electromagnetic process. For example, a pseudoscalar decay into 2 photons. And so the picture is actually very similar to the transition between a pseudoscalar meson to a vector meson, because for the photon one could treat it as a vector meson state, and using the light from wave function technique. So here one could actually take the light from wave function with a photon that obtained using the light from perturbative techniques. And then for the meson part, and one take the light from wave function solved non-perturbatively from the light from Hamiltonian. And so like this is a form factor we get for the eta C to that photon transition. And so calculating this process, one could also compare with experimental measurements. So, and even more, to just let you have a feeling of how useful doing this kind of calculation is that I think you may encounter the decay constant in some stage. So the way one gets the decay constant is also doing the same technique of the Lorentz vector decomposition as we did today. But it's slightly different and actually simpler. So for example, for vector meson state, so the current is from the Hadron matrix element would be from the vector meson and to vacuum, and the corresponding physical picture is that this vector meson would decay into a virtual photon and then the leptonic pair. And so here the Lorentz vector is in mu, and the coefficients in front it is not the form factor but the decay constant. So I think I will conclude here. So this lecture we studied the observables based on the light from wave functions of mesons, and continuing our first lecture. And so that's all. Thank you very much.
So, any question? Okay, I don't see any.
Thank you.
Yes, thank you. Any question from the people online?
Yeah. In principle, this technique is extendable to light mesons. I guess that the complication is that the number of higher order focus states that you have to include is greater, or what it is.
Oh yeah, actually it's also for the light mass. It's so it depends on what functions you have, like just as you said. So for light meson, if you have the wave function in the QQ bar sector, you just do exactly the same calculation, you get the form factor. It's just one may not trust it as much as one trusts the calculation of the QQ bar wave function from a heavy system. Yes.
Okay, then that's Meijian Li.
Thank you.
Thank you very much, everybody. I have uploaded the video. Okay, I don't know where anyone is. I have uploaded the videos already to the Indico, except this one, obviously. And the notes of, I guess, Fabio and the Tolga will come at some given point next week or whatever. Tolga said that he wanted to check. So thank you very much. I hope it was useful.